Hello everyone, welcome to today's session on Data Analytics with MATLAB. My name is Adam Fillion and I'm an application engineer at the MathWorks. My goal for this session is to show you how and why you should use MATLAB throughout your data analytics workflow. Whether that's early on in the process when you're importing or pre-processing data, whether you are more concerned with building advanced mathematical models, or if you're more concerned around how to take your analytics and incorporate them into production environments. Now I'd like to start off today by showing you an example of what the end product of a data analytics workflow might look like. So what I've tabbed over to here is a web page we've built for exploring our particular case study today. On the left you can see the state of New York, and on top of it we've drawn the different electricity grids in the state. And what this tool allows me to do is pick out one of those grids, and then when I click Generate Forecast, behind the scenes there's a bunch of MATLAB code running to grab data from multiple places across the web, stitch it together, run it through a neural network model, and generate some plots for us. So we can see in blue here what is the historical load in that region for the prior 48 hours, and then what is our forecast, our projection, for what we think the load will be for the next 24. And then if I want to look at a different region, let's say downtown New York City, well, we can pick that out, generate forecast, and now I get a forecast for what that particular region will be doing. So this example embodies a number of the characteristics that we find are very common in data analytics. Number one, this is all driven by business needs. This is a tool I could put into the hands of business decision makers, maybe the people running the plants in the different grids throughout New York, and they could use it to help them figure out at what level should they be running their different plants without needing to understand the more technical details of how we're making these projections. This is also a tool that we need to be able to open up to a large number of people for simultaneous access on demand 24 hours a day, 7 days a week, and we need to be able to update our analytics without taking our server down because, of course, power generation and demand never stops. So what we're going to focus on today is not how to build a web page like this. This is really meant to represent any arbitrary IT infrastructure where we want to integrate some analytics. What we're going to focus on instead is what's going on behind the scenes when I click that Generate Forecast. So how can we use MATLAB throughout this data analytics process to help us build this day-ahead forecasting system? So that's going to be our case study for today. We're going to put ourselves in the shoes of someone who is charged with building a day-ahead load forecasting system. Now, as we work through this problem, we're going to encounter a number of challenges that are very common in the world of data analytics. So, number one is aggregating data from multiple sources. Most people these days don't have just a single source of raw information. Most of their raw data is coming from several different places, if not many, and we need to find a way to easily aggregate them together into a single data source that's easy to work with. And of course, this data is rarely, if ever, perfect. So we need to find a way to identify anomalies or outliers, and we need to figure out what do we want to do about those. Once we've sort of handled our data, then it's time to look at how do we pick a model and how do we apply it and make some forecasts. And then lastly, how do we take the work that we've done and move it out into a production environment? So if we're going to get started on this data analytics workflow, the first thing we need to do is we need to figure out, well, where's our data coming from and how do we access it? So we have two sources of information today. One is the actual load in these different grids, and another is weather information from the different weather stations throughout New York, which you see with these little dots here. We're going to start by looking at the energy data. So this is publicly available data from the New York ISO. And you can see the way that they've stored it here. So they have this list of archived files, so a zip file for each month, and inside of these zip files we have a separate CSV file for every day. So we would eventually like to scale up and look at a large collection of these zip files over a number of years, but I always recommend prototyping small and then growing it from there. So the first thing we might want to do is grab a single file from a single day and figure out, well, how can we import and format that? So I'm going to tab over to MATLAB, where I've already done that. So we've got a file here from February. And if we want to just get a preview of what this file looks like, well, we can open up outside of MATLAB and see we've got sort of this tabular mixed format where this is stored. So the first thing I want to do is I want to get this into my MATLAB environment. If you've used MATLAB before, you might have found the import tool up here. But when I want to import a table of information like this into MATLAB, well, there's a really easy way to do that using a command called read table. So I can just give it the name of my file here, and it will read it into something called a table in MATLAB. So I can double click on this down here in my workspace, and we can see that once I read it into MATLAB as a table, it looks pretty much exactly like it did in the raw data file. So it looks like this is a pretty quick and easy way to read this from the raw data source into MATLAB, but we need to get this into the right format. So for starters, there's two different columns here, PTID and time zone, that aren't actually useful to me. So I want to remove these. Now, when we're working with tables, there's many different ways we might index into or reference different parts of them. So we could do it just like a normal matrix. So I could say for all the rows, and then I could say the fourth column, or I can actually give it the name PTID. And if I want to remove it, I'll set it equal to empty brackets, and then I'll delete it. Alternatively, I could reference this sort of like I would a structure, where I can see my table dot and then the name of the field. Set that equal to empty brackets. And there we go. Now we're down to just the columns that I care about, the timestamp, the name of the different zone, and what was the load at that timestamp in that particular zone. However, this isn't the most useful format for me. So if you see what the format here is, we have the timestamp, zone, same timestamp, different zone, same timestamp, and so on. And then once we get through all the different zones, then we iterate on the timestamp. What would be more useful to me is if I could pivot this around so I can see just for each timestamp, I can see in just a single row what are all the different zones and what's the load in them. So if you're new to any kind of concept or function in MATLAB, I always encourage you to check the documentation so we can do a quick search for a table if we're new to the table data type. And then we can also filter. Let's say I want to filter by products, so I want to look at just base MATLAB, and maybe I want to look for category pages that just summarize topics. So we can find one on tables. So these category pages are great. They organize different functions associated with the topic, properties, examples, concepts, and so on. So in this case, I'm looking for what's called the unstack. And so what this will allow me to do is sort of flip my table around. And I'd like to fill in the new table with the load. And I'd like to take my name column and turn that into the different columns. So now we can see, once I flip that around, now we can see for each timestamp, now the names have become the different columns, and we've filled it in with what is the load information. So at each point in time, I can see what was the load in all the different energy grids. So now that I've got it in this format, now I could pick out, let's say, a particular column. And I could easily plot this. I could write some commands to do that, or I could just come up to our Plots tab and click on Plot. So here we can see the value for the energy grid in the Dunwood region for this particular day. But of course, down here on the x-axis, right now I'm just plotting against the index number. I'd like to put my timestamp information down there. So you've been able to do this for many years in MATLAB. What I'm going to do here, though, is I'm going to convert my timestamp column into what we call a datetime. So datetime is a special container for handling date and time information. Here, MATLAB could take its best guess, but I always recommend specifying what the format is if you know it. So we're looking at the month, then the day, then the year, hour, minute, and second. Now, there's a number of useful things about this datetime container. You notice here it changes the display format a bit, but if I then select my timestamp and then the region, then when we plot it, now we automatically get the timestamp information down on our axis, and as we zoom or pan or look at particular data points, we can now see what was the actual timestamp at that point in time. So it looks like we've figured out, okay, well, how can we import our data? We can do that with read table. We can do a little bit with things like unstacking to get into the right format, and then using date time to get my timestamp information into a more useful form. But now, how can we take this and automate this process for doing it for many months at a time? Well, to help me with this, I've created a little script we're going to step through today. And so the first thing we're going to do is we're going to download these different files. So all I'm doing here really is inside of this loop here, we're specifying what's the file name on the server I want to read, what's its location, where do I want to put it on my local machine, and then we're using the command websave to save it from the web to my local machine. Now, I could do this in just sort of a normal for loop, but you notice here I use something called par_for. So par_for is a parallel for loop. It allows me to take iterations from a for loop and run them in parallel simultaneously. So if you notice when I first ran that, you see we got this message, we're starting a parallel pool using the local profile. So what this means is we are starting up what we call MATLAB workers. These are really just extra MATLAB computational threads, extra copies of the engine, running on my local machine that allow me to take independent tasks and run them simultaneously. And you notice that, well, if I want to download one file versus downloading a different file, there's no dependencies there. I can do them simultaneously. So I put this inside of a par_for loop, and now it's going to take advantage of my quad-core machine to download files in parallel. So you can see here we specified I wanted to read from January 2004 to August 2005. We went through and downloaded these 20 files. Then we simply said, okay, well, now we want to unzip all those files, and you can see we unzip them down here. And so now in our data folder, you can see we've got our different zip files that we got from the website, and we uncompress them, and now we get a different CSV file for each day. So then how can we aggregate them together? Well, it's a pretty similar concept. We're going to do this inside of a loop. We're going to read from a table. We're going to concatenate it on top of each other, so we're going to stack these tables on top of each other. Once we read and stack all of them together, then we can do an unstack on the whole data set all at once. We can convert to date time, and then we can sort it according to the dates so that they're all in order. But again, notice that reading from one file has no dependency on how I'm going to read from a different file. So as we're reading through our 609 different CSV files here and importing them into MATLAB, we'll do that in parallel with a par_for loop to help us speed up the process, get our analysis done faster. And then at the end, we can bring up a plot of what the results look like. So this again is the Dunwood regions. This is the same one we looked at earlier, but now we're looking at it for about a year and a half instead of a single 24-hour period. And so now we've got this larger data set, we can zoom in on a certain particular part. We can get a sense for what's going on here, so we can see we have sort of this cyclical behavior as we're going through time. But then you'll notice we also get these large spikes in our data as we're going through. So right now these look like some kind of anomaly. From what we have so far, we really can't say what's going on here, if it's a sensor giving us a bad reading, or someone took down a measurement incorrectly, or maybe something strange happened in reality. All we can say is that it looks like this is not part of normal behavior. So we have to ask ourselves a question. Do we want to try to build a single model that can understand both normal behavior and also predict when these types of anomalies will happen? Or do we want to find and remove these anomalies and focus first on understanding normal behavior? There is no one right answer. But what we're going to do today is we're going to try to identify these anomalies and remove them so that we can focus just on understanding normal behavior. So the question then becomes, well, how can we identify automatically what are all these different spikes in our system? Now, there's many different ways we might try to do this, with different pros and cons for different approaches. What we're going to do here is we're going to use a fairly simple approach that works pretty well in these types of situations. So we're going to grab our particular region for Dunwood and just look at that as an example. And the main function we're going to use here is what's called fit. So here we're going to fit a smoothing spline to our data. And then we're going to take a look at what's the difference between the original data and the smooth data. So let's zoom in on a particular section here. So in blue is the original raw data. In orange is the smooth data. And so you can see when we start over here on the left, it looks like we're in normal behavior, and so our smooth data is following the original data pretty well. But then when we get these large sudden spikes, our smoothing spline really shaves down those sharp corners, and we get a big difference between the two. And that's what we're seeing down here in the bottom plot, is we're looking at what's the difference between the smooth data and the original data. working under the assumption that when we see anomalies in our data, there are going to be these big sudden spikes. So this is a pretty simple technique, and it allows us to easily identify where we get these big spikes in our data that look like they might be anomalies. So the question then becomes, okay, so we've identified these, but then what do we want to do about them? Again, there's no one right answer. We might want to just remove these and just stick a blank value in there, something like a NaN, not a number. Or maybe we want to replace them with different values, maybe like a moving average or a linear interpolation. Refit a smoothing spline here to take a good guess at what that missing value maybe should have been. Again, that's very dependent upon the characteristics of your data and your domain knowledge of your particular problem and what's the best thing to do in that situation. For our purposes today, we just went through and just removed all these and just replaced it with a blank. And we're going to let our MATLAB functions downstream decide for themselves on what do they want to do when they get a blank in our data. So if you go and apply this to all of the different regions inside of New York, what we get in the end, if we go ahead and look back at Dunwood. So here you can see we went through and just imported a even larger set of data and cleaned it up. And you can see we got rid of all those really big spikes that we were seeing. And so now if we zoom in on our data, now we get just this regular periodic behavior that we're looking for. So we just stepped through that process for one of our two data sources, the energy data. We could go through the same process for the weather data, but in terms of techniques that you all can take home with you and apply to your own problems, which I'm sure are not exactly what we're doing today, there's not really anything new. It's applying all the same techniques for importing and formatting and cleaning up data, just doing it with a different data set. So for the sake of time, so we can focus on new things, I'll just load in what the final answer is for doing the same thing with the weather data. And so you can see we get the same kind of table with each timestamp, and then we get the temperature and dew point for the different weather stations throughout the state of New York. So now we've got our two data sources here, energy data and weather data. We figured out how to read them into MATLAB, how to then get them into the format that we like. We've cleaned up any anomalies that we wanted to remove. The question is then, how can we get these into a single format? Well, again, is one of the nice parts of working with tables in MATLAB is this is just a built-in function for joining tables together based on different conditions. Many different types of joins that we can do. Here I'm going to do what's called an inner join. So I'm going to join my energy and weather tables together, and I'm going to join them along a common axis. So in this case, it's going to be the date axis, the timestamp. And for an inner join, it's going to look at these two, look across their common column, and wherever both of them have something in common, whether they have the same timestamp, it's going to join them together into a new table. So here when I run my inner join, we can see now for each timestamp, I can see what was the load in each grid, and then what was the temperature and dew point for each weather station. So now in a single table, at each moment in time, I can see what was going on throughout the entire state, what was the load in all the different energy grids, and what was the temperature and dew point at all the different weather stations. Okay, so that kind of takes us through our first two bullet points. We looked at importing and aggregating and cleaning up our data. Now that we've done that, now it's time to start thinking about, well, how can I create a model so I can do some forecasting? So there's many different ways that we might try to build a mathematical model for a particular problem. Here, I'm just going to briefly introduce one popular branch of modeling called machine learning. Now, machine learning is very common when we run into a situation where either we have many different variables or our system is so complex that we don't know the governing equation. So I can't sit down and from first principles derive out an equation that will tell me exactly how the system is going to behave. And this is certainly the case that we're in today with our day-ahead load forecasting problem. But this is coming up in pretty much every major industry. So things like pattern recognition, finance, energy, biology, engineering, pretty much any field you're working in these days is finding uses for machine learning. So the next question we need to ask ourselves is, okay, maybe I want to take a machine learning approach, but then how many different models do I want to use, and what type of modeling techniques do I want. Well, we could try to model the entire state of New York as a single model, and then use which zone we want as an input, or we could try to model each zone independently and create a separate model for each zone. Again, there's pros and cons to both approaches. What we're going to do here, since each zone in New York behaves very differently from most of the others, is we're going to create a different model for each one. And we're going to start by looking at just a particular zone. So in this case, let's say I want to look at downtown New York City. So what I'm going to do is I'm going to pull out a subset of the data. So I'm going to grab the timestamp, what was the load in that particular zone. And then for downtown New York City, the weather station at LaGuardia does a good job of covering the whole zone, so I'm just going to grab this one weather station. And so now we have our new table with our timestamp, the load for that zone, and then the temperature and dew point. So we could take this and try to, just with this, try to do some machine learning, but I can tell you right now that's not going to work well. So what we want to do next is we want to try to build up a set of predictors, inputs, more information that our model could use to try to understand our system and make some predictions. So the first thing we might want to do, a really common technique when we're working with this timestamping information, is to break it apart into its different components so that we can vary them independently of each other. So maybe I want to take my date information, and maybe I want to pull out, let's say, the hour, the month of the year, the actual year itself, what day of the week is it, and then whether or not it's a weekend, and make these their own separate predictors so I can vary them all independently of each other. We can also take our temperature and dew point and pull them apart into completely separate predictors. And then maybe we want to take a look at the load data itself. So maybe we want to create some lagged predictors. So maybe the load at the current point in time will be highly correlated with what's going on at the same point in time 24 hours earlier. So here we'll go ahead and create that set of predictors. And now I can see for each row here, I have the load, and then I also have, just independently of each other, the hour, month, year, day of the week, whether or not it's a weekend, temperature and dew point. And then we also created what is the load at that point in time the prior day, and what's the load at that point in time same day prior week. So maybe this is a good starting point for our predictors. Last thing we might want to try do before we do any modeling is to create what's called training and test sets. So this is a really important concept because the whole goal of our modeling is we want to create a model that will work well in future conditions that we haven't seen yet. But of course, I don't want to create a model and then put it into a production environment and just wait for future conditions to happen to see how well it does. So what we're going to do here is we're going to take the data we have and split it into two groups. One group we're going to call the training set. We're going to use that to train or teach our model. The other group we're going to call the test set. And we're going to hold this aside and essentially pretend it's new data that we didn't know about ahead of time. After we've trained our model, we'll then take the test data, we'll feed it back through it, and see how well our model did on scenarios that it hadn't seen before. Now, there's many different ways we might split training and test sets, maybe doing random sampling or doing more sophisticated techniques like cross-validation. These are all certainly available out of the box with MATLAB. Here we're just going to do a simple split based on the point in time. So if it's May 2012 or earlier, we're going to train on that. And if it's later than May 2012, we're going to hold that aside as our test data. Okay, so now we've taken our initial data, we've created a set of predictors, split it up into our training and test data. Now we're ready to go ahead and fit a model. Now there's many different modeling techniques that are available with MATLAB in its toolboxes, simple things like linear regression or more sophisticated ones like bagged or bagged decision trees, random forest, and so on. For the sake of time today, we're just going to look at one, which is called neural networks. So the whole idea behind a neural network is it tries to mathematically simulate the way that actual neurons in the brain learn. So you can see here we get this little pop-up telling us how is the training going as we're trying to train through this different set. And we can open up some different metrics for us to look at. So if we want to look at a performance plot for how is this doing as it's training through these different iterations and trying to converge to the best solution. On the x-axis here, we can see what iteration is the model on as it's training. And then on the y-axis is the common metric for accuracy, the mean squared error. So we can see that the first couple iterations, we saw really rapid improvement, and now we're on just kind of this slow but steady improvement until it eventually converges. Now, one other thing I want to point you to is down here when we're training our neural network, you notice that there's this option here called use parallel and set equal to yes. So we talked about parallel computing a little bit earlier when we were looking at par-for loops, but there are many additional functions throughout MATLAB and its various toolboxes and add-ons that can also make use of this automatically under the hood. So when I'm training a neural network, there are many independent tasks going on as we're trying to train it and optimize it. And so in this case, I left that pool of MATLAB workers open that I talked about earlier. And here I'm going to give it just a single additional argument telling it, do I want to train in parallel? Yes, I do. And so this is going to automatically leverage my parallel MATLAB workers to speed up the training process and get my work done faster. So you can see that our model is, at this point, only getting gradually better. So we could let this just keep going and eventually converge to as best a solution it can possibly get to. But it looks like it's not making too much progress at this point, so we can go ahead and stop this early if we like. And then once we have our model, then we can go ahead and make a prediction on the test set and take a look at, well, what do the results look like. So here we're looking at the test data set. So this is the data that our neural network model had not seen before. In the top plot here in blue, we're plotting our neural network projection. So we're going through this whole roughly year and a half, 2 years worth of data, and doing a 24-hour projection at each point. And then in orange is the measured data. So this is the actual correct answers from downtown New York City. And then the bottom block down here, you can see the error, the difference between the two. So you can see we printed out here, on average, how well did our neural network model do for the training and test sets. And you can see for the test data, the data it had not seen before, it had about a 2.5% what we call mean absolute percent error. So on average, it was off by only about 2.5%, which is pretty good. But then you can see that in the error plot down here at the bottom, there are some places where it gets way, way off by thousands of megawatts. So for many people, myself included, this can be one of the more fun parts of this process because we get to play a bit of detective work. We get to look into these different situations and see, well, is there something that our model just isn't capturing here? So we can see there's a really big one here. So let's zoom in and see what's going on. So we can see for a couple days leading up to this event, our neural network in blue was following the actual response pretty well. And again, we're predicting what's going to happen 24 hours ahead of time. But then we run into a situation where our model gets just way off by thousands of megawatts for about a week. It takes a long time for it to recover and get back on track. So what was going on here? Well, we need to play a bit of detective work. First time I looked at this, I had no idea what was going on. So I saw that this was October 29th, 2012 in New York City. So I actually just hopped over to Google and I typed in October 29th, 2012 New York City. And this is when Hurricane Sandy hit. So if you don't remember Hurricane Sandy, this was a major weather event that hit the east coast of the United States, caused widespread devastation. And what we're seeing here is the effect on the energy grid, on electricity usage in downtown New York City in the aftermath of Hurricane Sandy hitting. So at this point we need to ask ourselves, well, what do we think about this? Do we think our model should be able to accurately predict what's going to happen when a once-in-a-century type hurricane hits? Or do we want to, again, focus just on understanding normal behavior, and maybe when we're evaluating our model, just throw this out and develop a more specialized routine for what's going to happen when we see a hurricane's coming and about to hit the city? That, again, no one right answer. It's very dependent upon your particular data, your knowledge of your domain, and how you want to handle these different situations. We then scroll around, see, well, are there other situations where maybe the model isn't doing so well? So we can see another one over here where we get off by a pretty wide margin. November 22nd, this was Thanksgiving. Right now there's nothing in our model that says when holidays happen, and holidays are pretty major deviations away from normal behavior. So we have to ask ourselves the same set of questions. Do we want to build a model that will understand both normal days and holidays, or do we want to have a special process for holidays. So we can keep digging into these different situations, trying to understand when our model is going awry. But eventually, we'll be happy with what we have. And it comes time to figure out, okay, well, how can I take the work that I've done and package it up and deploy it out for other people to use? So if I want to take the work that I've done in MATLAB and I want to package this up for people to use in different environments, I can package it up for components such as EXEs, Excel add-ins, C libraries, generic CTF, Java, .NET COM, and we can then take these and use them wherever we would normally use the components. Things like desktop applications, spreadsheets, databases, Hadoop, web applications. And this is entirely royalty-free deployment. Once you build these components, you can do whatever you like with them. It's a very simple point-and-click workflow, and it's the exact same workflow for all these different components. The general workflow here is you start by just building your MATLAB application to the point where you're ready to share it. Could be just a collection of MATLAB commands, might have some plots, could have a graphical interface. And then we run it through what's called the MATLAB compiler. So this will take your MATLAB application, do a dependency analysis on it to figure out what's everything it needs, and then we'll generate a wrapper around it and then compile it. So for example, if we were going for a jar file, it would actually generate some Java code as a wrapper and interface, and then compile it so I could use it just like I would any other jar file. I can then take this, I can pass it off to whoever I like as many times as I like. It's completely licensing and royalty free once you've built that component. But since it's just a wrapper around your MATLAB code, on the end machine, we also need to put what's called the MATLAB runtime. So this is just a collection of the MATLAB runtime libraries that is also freely distributable. Anybody in the world can go download it from our website at any time. So once you've built your end component with the MATLAB compiler, you can give it away to as many people as you like, use it however you like. There's no restrictions at all there. So this can be great for doing sort of desktop deployments or smaller scale environments. If I want to move it into a large scale production environment though, I might want to use what's called MATLAB Production Server. And so this is what we're actually using behind the scenes for the web page that we built for today. So let's take a quick look at what's the underlying structure for the application that we built. So the front end of our web page was actually built in JavaScript. So this is running on an Apache Tomcat server, which is running on Amazon EC2. When someone needs our MATLAB analytics, like when they click that Generate Forecast button, this calls into what's called the MATLAB Production Server. So the MATLAB Production Server is all designed around making your MATLAB analytics available to a large number of people simultaneously on demand, letting us do hot swaps where we can update things without needing to take the server down, and giving us a place where we can easily and centrally manage a large number of different MATLAB components and versions of the MATLAB engine. So when we call into the MATLAB production server, there's a request broker. So this does load balancing. So when we get massive numbers of requests coming in, it's automatically balancing for us how to manage that large number of requests. And it will load up the CTF file that we need. Now this could package really just about any MATLAB code that we want. In this case, it's actually going to, using our MATLAB code, grab the data from the energy website, grab data from our weather website, and then it's going to load up our predictive models, which we trained offline in our MATLAB desktop. Now, there's a couple of key benefits of setting up our system this way. One of the big things of using the MATLAB production server like this is it allows us to decouple our analytics from our application. So if I need to update what's going on in my CTF file here, if I need to add a whole new data source, if I want to change the way I'm cleaning up my data, if I want to update my models, well, as long as the way that the Java code is going to call this, as long as the function signatures here in my MATLAB code don't change, I can change whatever's under the hood, and I can just drag and drop a new version of it into the production server. And our application server doesn't need to know anything about it. It doesn't need to restart. In fact, the people who are using this web page don't even need to reload the web page. Just the next time they click that Generate Forecast button, next time they need our analytics, it's going to go grab our new stuff automatically. So I just want to wrap up with a couple key takeaways today. Number one, data preparation can be a big job. There's some people out there who spend as much as 80% of their time just trying to get their data in the right format, and there's a lot of tools in MATLAB to help you make that easier. There are many different predictive models available, and you can very easily and rapidly iterate through many of them to figure out what's going to be the best one for your particular problem. Parallel computing is a very easy thing to integrate into many different parts of your workflow to speed up your analysis and handle larger data sets. And once you're ready to take your MATLAB work and deploy it out to other environments, you can eliminate the need to recode your MATLAB algorithms by using the MATLAB compiler to package it up into an easily shareable format. So that's about it for me today. Thank you all for tuning in.